Okay, so today's notes are on function operations. It's section 66A. I decided to break this section into two. So today we're just focusing on function operations, and our language objective is to use the correct terminology to explain those. So before we jump in, I want to do a quick review of function notation. So function notation, as a reminder, is when we write f of x equals some function, or g of x equals some function, or you could use h of x or any real letter t of x, whatever you want to use. But it's when you write this, which implies the whole function. So if I have this whole thing, it implies the whole function. So if I have f of x with nothing plugged in for x, it implies the whole function. So that's if nothing is substituted. So this could equal any function equation. It could be x squared plus 3, x plus 1, x minus 4, square root of x plus 16. Like, it doesn't matter what this, or it does matter, but this can be any function. But the point is, this represents the entire function when it's written like that, if nothing is substituted. Or if you plug something in for x, so if something was plugged in for here, so say there was a number, that would be what has been substituted for x. So if there's something plugged in, that's what has been substituted for x. And if you've plugged something in for x, then that would represent the y value for the substituted x. Or that corresponds with the substituted x value. So if a number has been plugged in, it means the value you get when you plug in that number for x. So that's the second part. But if nothing has been substituted, then f of x represents the whole equation. The same thing applies to g of x. It's just a way of writing equations and denoting what you've plugged in for x, or writing the whole equation as just a whole equation. So the reason I review that is because what we're going to do today is function operations. So we're going to start with addition with two functions. So if I'm trying to add two functions, I could write it like f plus g of x. And what that means, or what that is equal to, is the function f of x plus the function g of x. So you just take two whole functions and add them together, combine your like terms, and that's what the addition of two functions is. Subtraction with two functions is the same thing. So it'd just be f minus g of x, and it'd be equal to the function f of x minus the function g of x. Multiplication, again, you're just performing these operations with these whole functions. So this would be f, I'm just going to write a dot. Notice that it's a closed dot. This will come up next 66b. So make sure when you write multiplication, it's a closed dot. And that would just be equal to the whole function f of x times the whole function g of x. And last but not least, division, it would be f divided by g of x, and that'd just be equal to the function f of x divided by the function g of x. So that's the actual process of adding, subtracting, multiplying, dividing is not all that tricky. It's just combining like terms or simplifying expressions. What I'm guessing will be a little bit trickier for people is talking about the domains. So when we start focusing on the domains of these functions, this is a reminder of the domains, which are the x values of the sum, the difference, this product, or quotient, are the x values that work in both equations, or the x values that are in the domains of both functions. So in order for these composite functions, or the domains of these the domains of these function operations is going to be the original domains, the combined original domains of the original functions that you combined with these operations. The only thing that's sort of like a little asterisk on this, or a little note you need to make, is if you take the quotient, so if it is the quotient, the domain cannot include a value that would make the denominator 0. So obviously when you are dividing something, you can't divide by 0, that's never allowed. So the same thing applies when you are performing operations with functions. If you would have a value of x in the denominator that would make it 0, that can't be in your domain. The whole point of having domains is knowing what x values you're allowed to plug in and get real answers. So you can't plug in 0 to the denominator, so you need to account for that when you're defining your domain. So this is all pretty abstract. Let me flip the page and show you an example. So we're going to start with the easier of the operations, addition and subtraction. So our first example, we are going to let f of x equal 4x plus 7, and g of x equals the square root of x plus x. And I want to know what are f plus g and f minus g, and what are their domains. Okay, so first thing, I'm going to find the sum. So to find the sum, I'm literally just going to take f plus g of x, and I'm going to write f of x, so 4x plus 7, and I'm going to add g of x, which is the square root of x plus x. And since I'm adding them, I don't actually need these parentheses, so all I need to do is combine my like terms. So I get f plus g of x equals, I have an x and an x here, so that becomes 5x. Then I have plus the square root of x plus 7. The ordering doesn't necessarily matter. If you wrote plus 7, then plus square root of x, that is equivalent. I choose to write x's first and then constants last, which is why the 7's on the end. But this would be our sum of those two functions. So then let's find the difference. So this is f minus g of x. So again, I have 4x plus 7 minus the square root of x plus x. So this time, since there's a negative in front of that set of parentheses, I need to distribute it. So I get 4x plus 7, which I guess doesn't actually need to be in parentheses, minus the square root of x, and then I get minus x, because I distribute it to both parts of that expression. And then I combine my like terms, so I have a negative x and a 4x, which becomes 3x minus the square root of x plus 7, and that would be the difference of those two functions. So f minus g of x would be this. Sorry, I didn't box my last answer, but I'll go back and box both. So those are f plus g and f minus g, and now I need to determine the domains. So I'm going to start by determining the domains of my original functions. So if I'm looking at f of x, so the domain of f of x, there aren't any values that would give me undefined if I plug them in for x. There's no values of x that I could plug in and get undefined. So it would be all reals. So the domain is all real numbers. And I'm going to note that's because there aren't any x values that would make it undefined. So turning to g of x. I know f of x is all real numbers. G of x, if I look back up here, since there is a square root sign, the domain here, I know I can't plug in a negative number to a square root and get a real answer. I'm not allowed to do that. So I know that I can't plug in any negative numbers for x. Because of that square root sign, there are no x values I can plug in, or no negative x values I can plug in and get real answers. So I know that the domain is x is greater than or equal to 0. Because if x were negative, you would have a negative square root, which is not allowed. So I know that for this one, the domain is x is greater than 0. So then my last step, determine the domain for the new functions, for the final domains. And since, as we saw on our last page, I know that the domain has to meet both of the original domains for my functions, I know that the domain for both of these, they have a domain of x is greater than or equal to 0. Because it has to include the more restrictive domain. All right, so I'm going to flip the page and do one more slightly trickier example with multiplication and division. So I'm going to flip the page. For this example, I want us to let f of x equal x squared minus 9 and g of x equal x plus 3. And I'm asking, what are f times g and f divided by g and their domains? All right, so to do this, I'm going to first start by determining the product. So here I'm going to do f dot g of x, and that's going to equal f of x, x squared minus 9, times g of x, x plus 3. And all I need to do here is multiply those or FOIL that out. So I get f dot g of x equals x cubed plus 3x squared minus 9x minus 27. There aren't any other terms I can combine, so that is my product of those two functions. That's all I have to do there. Pretty straightforward. So then I'm going to continue on and determine the quotient. So when I do that, I have f over g of x, and that's going to equal x squared minus 9 over x plus 3. And I'm going to pause here for a second and just note that we're going to have to come back to this original one, but for the process of simplifying, I'm going to keep going and simplify this fraction because I know I can factor x squared minus 9, the difference of squares. So I'm going to add and simplify. So this factors to x plus 3 times x minus 3, and that's still over x plus 3. So then I know that those two terms, x plus 3 divided by x plus 3, I can cancel those out, and I get f over g of x equals just x minus 3. So my fully simplified quotient there would be x minus 3, but I'm going to come back and add a little stipulation to this in just a second, so when we get to our domains. So for 3, I'm going to determine original domains, just as we did before. And if I look at both of these, again, there's no square roots, there's no fourth roots, there's no weird roots here. So I can go ahead and say that the domains, original domains, are all real numbers. So my original domains are all real numbers. So the domain for the product, so f dot g of x, domain is all real numbers. So that's my domain for the product. The reason I didn't add the quotient, so for the quotient, the domain would be all real numbers if I just had to look at what the original domains were. But if you remember from that other page, I noted that our denominator can never equal 0, or the original denominator can never be equal to 0. So step 4, I've already started, but I'm going to determine new domains. And I'm going to put a little star here because the quotient, you need to check for values that make the original denominator the initial denominator equals 0. So if I go back, I know my original denominator was x plus 3. So I know for f over g of x, x plus 3 cannot equal 0. So I know x plus 3 cannot equal 0. So I know that x cannot equal -3, and that is going to be my domain. Because it would be all real numbers except for the value that would make my original denominator equal to 0. So x cannot equal -3, so that's the little stipulation I should add up here at the end, because when you write the equation, you need to include or adjust for that fact so that even though this looks like it should be all real numbers, you know that x can't equal -3. All right, that's all for today. Make sure you write down questions, comments, concerns so we can go over them together in class.